you built this nice Turing machine. You want to call up your friend and tell them all about this. I've got this fancy Turing machine to do graph connectivity. Okay, so what you have to do is you have to first now take all the states and the symbols that can appear and all the various instructions, okay, and encode it into your binary string and then send the binary string to your friend over the email. Okay, it's a bunch of zeros and ones. Okay. But there is a more fundamental problem here. What's the fundamental problem? The fundamental problem here is, okay, great. So I built a Turing machine to solve this problem. Now I want to change the problem, to solve another problem. Okay, nice. Good job, buddy. You solved this problem. You want to solve another problem? Build another Turing machine. Okay. What does building another Turing machine mean? Build a CPU with states, and it's got its tape, and now you put the input on the tape, and it'll tell you yes or no whether the graph is connected, or yes or no for whatever other problem. And you want to build it, or you want to solve another problem? Build another Turing machine. Basically, what we're saying is a Turing machine is a computer. Okay, and every time you want to solve a problem, build another computer. That doesn't look like computing today. We don't build another computer for every problem that we want to solve. Okay. So something is missing if we're going to link this, baby machine with these primitive capabilities to this sophisticated single machine, which we call today a computer that can solve all kinds of problems. Okay? And there's just one more ingredient that we need to add, which is, this notion of programmability. Okay? So the only difference between essentially our current Turing machine and the guy that's sitting on your desk is the guy that's sitting on your desk is some fixed architecture, some fixed machine, and what you do is you feed it a program. Okay? Here we have a fixed machine, a fixed architecture, its states and the way it moves state, and we feed it an input. Okay? So the difference is in your computer, which is exactly this guy, you're not feeding it an input, and so you don't have a new computer for every problem you want to solve. You feed it a program, and then into the program you feed an input. Okay, so somehow, in current computing, the program plays the role of the Turing machine, okay, and the input to your program is the input to that Turing machine. So basically what we're saying is that in modern computing, there's the box, and you feed into this guy the program, so let's call this a computer, and you feed into this guy the program, and into the program you feed in the input. And then the program tests for graph connectivity and says yes or no. Okay? So there's some magic going on here where somehow this program is related to my Turing machine, my algorithm, and then the computer is somehow executing the program. So you can think of your computer as a programmable box, and we will get to that computer if we can build a programmable Turing machine. And I'm going to now tell you what that is. So next topic. Programmable Turing machines. Wow, oh man, we're flying. So the next stop is the programmable Turing machine. Let me tell you about the Programmable Turing Machine. We call it a Universal Turing Machine, and for short, UTM. TM for Turing Machine, U for Universal. Okay, and this is basically, what we have sitting on our desks, a Programmable Turing Machine. Okay, in fact, what I'm about to tell you is actually a little bit more powerful, a little bit stronger than, anything that we can have on our desk. Okay, and so, when we study the capabilities of this thing, if there are problems that this thing cannot solve, then you can be sure, you can bet your bottom dollar that the thing on your desk cannot solve it. Okay, and what's the basic idea, and why do we call it a Universal Turing Machine? So the basic idea is there exists a Turing machine which can simulate any other Turing machine. Okay, and now we need to parse that. What does that mean? So in some sense, there's some Turing machine that can simulate any other Turing machine. So in some sense, that this fancy Turing machine, which we call the Universal Turing Machine, has to be able to know what's going on. What is that other Turing machine? So in some way, that other Turing machine must be fed in to this Universal Turing Machine as some kind of an input. Okay. Well, that shouldn't surprise you at all. So you should be familiar with the concept of something like a program taking as input another program. That's exactly what a compiler does. It's a program, a compiler is a program, takes as input another program, and then does something, that depends on the other programs. For example, checks its syntax and then converts it to machine code instructions and so on and so forth. Okay, so that's what a compiler does. It takes as input another program. So no surprise, there exists Turing machines that can take as input another Turing machine. But how does a machine take as input another machine? Does it just gobble it up? No. So we have to look more closely at what is a Turing machine. So remember, we have a Turing machine M, and now this is where the encoding of the Turing machine becomes very important. Okay, we can convert any Turing machine M into its description, the encoding of M. What is its description? It's just a binary string. Okay, it's just a binary string. Okay, good. Now, you have a Turing machine, it can take as, it processes some input. Let's call that input W. Well, what is that? W is just a binary string. Okay. So now here's an interesting quantity. Let me ask, what is the following? So I'm going to take my description. Okay, put a punctuation character just to make things easier. Okay, and then I'm going to attach my input W. So what is that? Take a couple of seconds. Think about it. 1, 2, 3, 4, 5. Well, if you're coming back, well, I'm not really after a sophisticated answer. This is just a binary string. Assuming that, we have encoded the pound punctuation character into some binary encoding, like, ASCII code. Okay. So this is just a binary string. Okay. And, it's just that it's a very special binary string. It has two parts, two essential parts. One, which is the description of a Turing machine, and two, which is the input to this Turing machine. So this is a fancy binary string. And remember, a Turing machine is a machine that should be able to take as input any binary string. Okay? Because what a Turing machine does is it solves some problem. So it takes as input any binary string and says yes or no whether it belongs to some language. Okay? So since this is a binary string, it can be the input to a Turing machine. Okay? So I could, for example, initiate a Turing machine's tape, okay, which has, the beacon symbol, okay, star, okay, and, then I'm going to list out this whole string. Well, this whole string consists of, the part that encodes my Turing machine M, okay, and then let's say a punctuation set of bits, and then the part that is my string W, okay, and, for good measure, I'll show you some blank slots as well. Okay, so that's a perfectly valid state of a Turing machine's tape in which the input is this complicated thing, but at the end of the day, it's just a binary string. It just so happens that this binary string has two parts, one which encodes a Turing machine and one which is a string W. Okay, no problem. Okay. Now, there's nothing fancy here. Now, let's have a look at what M does. Okay, and for the moment, we don't care if M is a decider or a recognizer. Okay, so when M operates on W, okay, so if M is a Turing machine running with input W, which is, this would be represented by the picture, here's M, and it starts on some tape, okay, and it starts at its beacon symbol. Okay, and it starts with W on the tape. So it's got the input W, and we can put some blanks for good measure. So if M operates on W, this would be the starting configuration where M is getting ready to operate on W. It bumbles around, roams around, changes states, reads, writes, and so on, and eventually will do one of three things. It will either halt and say yes. It will either halt and say no. Now, if it was a decider, those are the only two options, but it could be a recognizer, so it has the possibility to infinite loop. Okay, so for the moment, we're not, narrowing our discussion down to just deciders. We're considering a general Turing machine M, and one of three things could happen. Okay, and this is the situation with M running, on its input W. Well, okay, now this Turing machine U that's going to have the capability to simulate any other Turing machine is going to be looking at an input like this. Okay? Because if I'm going to simulate any other Turing machine, I need to know what's that other Turing machine. And there's a perfectly valid way of telling the universal Turing machine what's that other Turing machine. I just feed it in as part of the input. So you can imagine another Turing machine, okay, not M, but this guy, U, okay, sitting here getting ready to start work. Okay, and its input starts with a description of a Turing machine. Okay? And its input, and then follows by a string W, which is supposed to be the input to this Turing machine. So, okay, W is the input to M. W is the input to M. M W is the input to UTM. Okay. MW is the input to UTM. So that's what's unusual here. The input to this fancy Turing machine, which I'm going to sort of briefly describe, is a much bigger string than W, because this much bigger string also contains a description of the hypothetical Turing machine that I would like to run on W. Now, the goal of this universal Turing machine is to be able to pretend to be able to simulate what would have happened if M ran on W. Okay? So, when M runs on W, one of three things could happen. What I would like is that when UTM runs on this, so when UTM runs on its input, which is much bigger than W, when UTM runs on M pound W, it should do one of three things. Okay? It should either halt, okay, with, and say yes, if M of W is equal to halt and yes. It should halt and say no if M of W equals halt and say no. And it should infinite loop if M of W is equal to infinite loop. Okay? So let's see whether that makes sense. Listen, M can do one of three things. Okay? Halt yes, halt no, infinite loop. Okay? Now, I would like UTM to simulate M running on W. Okay? So in order to tell UTM, simulate M running on W, I feed it M, because it needs to know M, and it needs to know W. Okay? And it should halt and say yes if M would have halted and said yes on W. It should halt and say no if M would have halted and said no on W. And it should infinite loop if M infinite loops on W. So that's what it means, and that's exactly simulating M on W. It's producing the same outcome that M would have produced on W. Okay. You can effectively think of this as UTM is running the machine M on W. UTM is running the machine M on W. And it turns out that we can build a fixed universal Turing machine. Why do I say fixed? So you can't change this Turing machine if you want to change the Turing machine you want to simulate, or if you want to change the input W. So there is a fixed Turing machine that can simulate any other Turing machine on any input. Wow! So let me show you, at least at a high level, how this fixed Turing machine would work. And you can read the text for more details. Basically what's going on is, if M were running on W, okay, M would at all times be in some state. Okay? So the states are somewhere here in the description. And so what UTM is going to do is it's going to roam around, okay, and see, what's the description of M. It can roam around and see what's going on with W. But when M runs on W, at any time it's in some state. So, we could mark the state that it's in with, let's say, a red square. Okay, and anytime the head of M is somewhere in its state, in the state that it's operating. So the head of M could be at the beacon symbol, which would be this pound, or it could be somewhere in W. So we can mark where's the head of M. So think of this as M's state. Remember, a universal Turing machine has the ability to mark. It has the ability to write. So M's state, and you can think of that as M's head. So UTM has a head. Okay, but it can pretend, it can mark where M's head is. Okay, so that way it can keep track of where M is on its tape, on its input, and it can keep track of where M is in terms of its state. Okay. So now what UTM does is it roams around, then it comes to, okay, where's M's head? It comes to M's head and sees, oh, I'm reading a 0. Okay, I'm reading a 0. So now it roams around around M and finds, okay, what's my current state? Okay, my current state is where I've marked it. I remember that I read a 0. So I remember that I read a 0. I look at my current state, and now I look around for the instruction that tells me what to do for this current state and whatever symbol I read. I can remember the symbol I read by transitioning to a state. Okay. So once I find the instruction, I execute the instruction. If that instruction will tell me, maybe move the head, so I'll move this mark. It will tell me move my state, maybe I'll move this mark. And it might tell me to read or to write something here, so I'll write something here. And now I've changed the state, I've moved the mark, and I'm ready to, go and process another step in the execution of M, where I'll then go and see, okay, where's my current head position? Okay, where's my current state? And so on. So basically UTM uses the tape to perform the computation of M on W by roaming around and marking appropriately. So you can see the text for some of the details. But the miracle of today is that you can build a UTM with a small number of states, maybe something like 20 states. Okay? You can build a UTM with a small number of states that can perform this simulation, and it will work flawlessly for any input Turing machine M and any input W. Programmable Turing machine takes as input a Turing machine and the input to that Turing machine and pretends and runs it for you. Bam! We have the programmable computer that is on your desk. Okay. Think of UTM as the computer, the box, the hardware. Think of UTM as the big computer. Think of this guy M as your program. You write a program, and then your compiler converts it into this bit string. And then into your program, you feed an input, for example, a graph. Okay. So your program is compiled into this string. Your input graph is compiled into this string. And these two together are what your computer, your box, your universal Turing machine simulates. It simulates your Turing machine running on W. So what's the beauty here? You don't need a new box when you want to solve a new problem. You just send in a different description of some other Turing machine that solves your other problem. So this guy that's fed into UTM, this is what we call a program. This is what we call a computer. Okay, and this is the input to your program. And there we have the theoretical model of a computer. Bam! Okay. And so the basic thing that we have to get used to is that a Turing machine can take as input another Turing machine. And so now I'm going to erase, okay, and I'm going to describe a whole bunch of interesting problems, okay, that we would like to solve. And then we're going to go step by step and see whether or not we can solve them. Okay. So let's erase. Bam. So excited! We have built a theoretical model of a computer that takes as input a program, i.e. a description, a binary description of another Turing machine, which is your program, and we compile it into the actual binary string.